Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. This is part 2 of the two-part series on sizing of centrifugal compressors. In the part 2, you will understand the performance parameters and learn how to size a centrifugal compressor. In the part 1 of the sizing of compressor video, we learned the steps involved in the sizing. In this video, you will understand the parameters that define the compressor performance. Also learn through a worked example how to size centrifugal compressor. What is the most important performance metric in the evaluation of compressor performance? Everything else remaining the same for a given gas mixer, the one metric which is the most important is compressor efficiency. That is, for a given compression ratio and inlet condition, the compressor efficiency matters the most. Doesn't it make you interested in knowing more? I am sure you are. It is a knowledge that is going to remain with you for the rest of your career. So don't drop out in the middle. Hold on till the end of the video. Efficiency impacts the power consumed by the compressor, that is the horsepower. Power consumption is a recurring expense. Lower the horsepower, lower will be the cost of production. To estimate polytropic efficiency, you need to understand the parameters that define the compressor performance. Centrifugal compressor performance depends on the performance of the impeller, which in turn depends on the blade style. The impeller performance is evaluated in terms of flow coefficient and pressure or head coefficient. Flow coefficient is defined as the ratio of the actual inflow to the compressor to the impeller characteristic or machine flow. Machine flow is a function of impeller speed and its diameter. Thus, the flow coefficient expresses the relationship between the actual flow rate to the impeller dia and its speed. The units for the various terms for the flow coefficient expression are given here. Stage efficiency increases with increasing flow coefficient because the channel width increases and the friction losses decreases. Compressor manufacturer provides polytropic efficiency versus flow coefficient curve for a specific compressor. This graph illustrates the relationship between polytropic efficiency and flow coefficient. The increasing efficiency with flow coefficient reaches a maximum when the flow coefficient in the range of 0.06 to 0.1. Thus, flow coefficient is an important performance parameter to manipulate and determine the size and speed of the compressor. It has a striking influence on the efficiency. This graph illustrates the trend in compressor efficiency over the years. From 1970 to 2000, the efficiency has improved from 75 to 85%. By 2025, further ongoing improvement in impeller and diffuser design will lead to efficiency to reach 88 to 90% from the present 85%. For a multi-stage compressor, the first stage should use high flow coefficient impeller, and the intermediate stage should use medium flow coefficient impeller, so that use of low flow coefficient is limited to the last stage. This is due to the fact that the volumetric flow is progressively getting reduced as the gas gets compressed as it flows through the stages while the mass being constant. This figure illustrates the high flow coefficient at the inlet and low flow coefficient at the discharge end of the compressor. Note, the impeller width is getting smaller from the compressor inlet end to the discharge end. Another important compression performance parameter is head coefficient. Head coefficient is expressed as a ratio of polytropic head to the Euler's head. The units for the different terms in the coefficient are given here. The term head coefficient, also called specific head, is a ratio of kinetic energy of the fluid under the polytropic head to the kinetic energy at the tangential speed of the impeller. Let me now walk you through the worked example. The worked example deals with the estimation of power required for a multi-stage steam turbine driven centrifugal compressor. Problem description. A petrochemical plant proposes to install a centrifugal compressor to liquefy the propylene gas produced in the olefin plant. Figure 4 next is an illustration of the 4-stage centrifugal compressor that the plant has finalized. The first product propylene gas from the upstream unit enters a section of the compressor stage 1. The compressor stage 2 and the stage 3 draws additional gas from 2 other sources from the plant. The 3 sources of propylene gas to the compressor section are chillers 1 0.19 million kg per hour at 1.65 bar pressure, chillers 2 and propane propylene splitter 1.548 million kg per hour at 5.42 bar, chiller group 3 and reboiler 1.656 million kg per hour at 8.3 bar. A major part of the compressed gas is withdrawn from the discharge of the compressor stage 3 for condensation in a heat integration system in the plant. The balanced gas flows out of the discharge of the stage 4 and is liquefied in a separate condenser. This figure illustrates the schematic representation of the 4-stage centrifugal compressor. The table 1 and 2 provide the flow rates and thermodynamic properties of the gas to the various stages of the compressor. The plant intends to use a steam turbine drive for the compressor, which can use 42.5 bar G high pressure steam available in adequate quantities from the utilities unit. This sketch illustrates how the 4-stage compressor is integrated with the steam turbine drive. The steam supply to the turbine is 42.5 bar. Steam is extracted at 4.2 bar from the turbine. This table presents the properties of gas at various stages of the compressor. You are required to size the compressor for this service. That is, to estimate the power required for the individual stages of the compressor and the total quantity of steam required by the turbine. Now the solution part. The calculation procedure involves estimating the power required individually for the 4 stages and then summing up the individual power to estimate the total power required. If you have a process simulation package with you, you can solve the flow sheet. But the idea behind giving you the manual calculation procedure is to understand the stepwise calculations the black box is doing. Believe me, if you want to understand the process simulation effectively, you need to know the nitty-gritty of the calculations. At this point, I would like you to recall what you have learned in the part 1 of the compressor sizing. The first step is to determine what is the pressure ratio for the individual stages. The liquid propylene is used in the chillers in the plant to cool down various gas streams before dehydration and cryogenic distillation and separation is done. The propylene functions as a refrigerant. Hence, the operating pressure of the chillers is fixed by the temperature of the gas to be cooled. This sketch illustrates how the various low temperature heat loads in the plant is integrated with the compressor inlets. Compared to the operating pressures of the chiller and other units, the system resistance was less. The propellant chiller operating temperatures and refrigerant side corresponding operating pressures determine the inlet pressures and intermediate discharge pressures of the compressor. These are estimated and listed in the table here along with the vapor capacities based on the refrigeration temperature and load. The final discharge pressure is decided by the available cooling water temperature. The cooling water supply is 38 degrees centigrade and the return is 48 degrees centigrade. In the worst case scenario, the temperature can go to 55 degrees centigrade. Accordingly, the final discharge pressure is fixed. From the total estimated power of the compressor and the steam turbine data, the steam turbine power consumption is estimated. Let us first determine the power required for stage 1. The stage 1 inlet temperature is minus 35 degrees centigrade. Compressibility factor Z1 is 0.949 and Z2 0.912. The pressure at the inlet P1 is 1.65 bar absolute. Discharge pressure P2 5.42 bar absolute. Ratio of specific heat at inlet K1 1.22. Ratio of specific heat K2 at outlet 1.21. Specific heat ratio average K average is 1.215 and molecular weight is 42.08. With values of all the input parameters known, we can estimate the power required in the first stage using the equation given here. The polytropic constant N is obtained from the polytropic efficiency and adiabatic constant K. The relationship between the polytropic constant N, adiabatic constant K and the polytropic efficiency is presented here. Substituting the values of K and efficiency in the above equation, you can get the value of N. The value of N obtained is 1.2606. Now you have the values of all the input variables including N to estimate the power required. The calculated power for the first stage is 3266.8 kilowatt. The actual work done or the brake horsepower is obtained from the expression polytropic work done divided by the polytropic efficiency. So the brake horsepower for the first stage is 3816.36 kilowatt. Other mechanical losses in the compressor system will account for some additional drop in efficiency. Take 4% efficiency loss to account for these losses. The estimated power for the stage 1 is 3975.37 kilowatt. Similarly, the power for the stage 2, stage 3 and stage 4 are estimated. You can calculate the power required for the 4 stages in an Excel sheet easily. The values obtained for the 4 stages are presented in the table here. The total estimated power for the compressor is the sum of the estimated power for the individual stages. And this works out to 31,058.65 kilowatt. The next step is estimation of steam turbine steam demand. The turbine inlet steam pressure is 42 bar. Steam inlet temperature to turbine 395 degrees centigrade. Steam extraction pressure is 4.2 bar G. The enthalpy of inlet steam at 42 bar G and 395 degrees centigrade H1 equals 3212 kilojoules per kg. The enthalpy of inlet steam at 4.2 bar G H2 equals 2546.27 kilojoules per kg. The change in steam enthalpy H1 minus H2 is 665.72 kilojoules per kg. The quantity of steam required for the turbine can be obtained from the energy balance using the expression here. So the calculated value of steam required for the turbine is 46.65 kg per second, which works out to 167.95 tons per hour. Please subscribe to our channel and get updates on the upcoming videos by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation of part 2 of the 2-part series on sizing of centrifugal compressor. Hope this presentation with narration and animation was useful. I welcome your comments, if any, about this course. Share with your friends and colleagues to reach out to a large number of career-oriented professional students. Thank you for watching.